Hello.
Hello.
Okay, we'll do number theory problems today. These are all previous year's AMC questions. So
Yeah.
try them out. The first one is the LCM.
Oh wait, before, can I just ask a question on the homework
Mm-hmm.
problem? Okay,
Which
so
homework problem?
you gave me two homework problems to do. The first one was prove that a factorial times b factorial divides a plus b factorial. And then the
Mm-hmm.
second one was let n be a positive integer. The product of prove that the product of n consecutive integers is divisible by n factorial.
Okay.
So I needed help on the first one. So the a factorial times b factorial divides a plus b factorial. So what I did so far is that you can write a plus b factorial as like a factorial times a plus 1 times a plus 2 all the way to a plus b. So you get that it's divisible by a factorial, but I don't know, I'm not sure how to like get the b factorial from the remaining a plus 1 times a plus 2 times all the way to a plus b.
Do you know what is the meaning of NCR?
Uh, yeah, it's like choosing r numbers out of n. Yeah, n factorial times n minus r times r. Yeah.
Number of ways of choosing R things out of N things, right?
Right.
Obviously, this number is going to be an integer.
Yes.
So we can prove it very simply by saying what is A plus B C A?
Oh,
Number of
a
ways of choosing A things out of A plus B things.
yeah.
By definition, it will be, and by
Oh,
definition, this is an integer.
oh, okay, yeah, I understand. Okay, that makes sense.
If this is an integer, that means this thing divides this thing.
Oh, okay. I was like expanding it and trying to find it.
You can prove it by expanding, but then you will have to use induction. Uh, you can prove it by expanding also, but you'll have to use induction. You'll have to say that uh, for example, the result is true. The result is true for a plus b less than equal to 1
Mm-hmm.
because 0 factorial is same as 1.
Yeah.
In any case, in this case, a factorial b factorial will divide a plus b factorial because this will be either 1 factorial or 0 factorial, which are both 1. And then these will be also 1 into 1 only.
Right.
So the result is true for the base case. This is the base case where a plus b
Yes.
is less than equal to 1. We will assume that the result is true when a plus b is equal to n minus 1. Assume that in that case, basically a factorial b factorial divides a plus b factorial. And now from here, we have to use this to prove that if a plus b is equal to n, then also the result is true.
Right.
So, so basically, we'll try to calculate what this is divided by a factorial b factorial, and we can write this as uh, a plus b into a plus b minus 1 factorial and mm, or actually let's just check the value of what is a plus b minus 1 factorial divided by a minus 1 factorial b factorial plus a plus b minus 1 factorial divided by a factorial and b minus 1 factorial. Let's just check what is this RHS, whether it is equal to this or not. So you can take this common, right? First numerator.
Yeah.
Numerator is common, you are getting 1 by this plus 1 by this. So
Right.
let's see what happens there when we simplify. Actually, other things also can be taken common. You can take a plus b minus 1 factorial by a minus 1 factorial b minus 1 factorial common, and inside you will have 1 by b plus 1 by a, right?
Oh, right, right, yeah.
So this becomes a plus b by ab, and now you can see why if you multiply a plus b with this, the top part is a plus b factorial.
Yes.
And if you multiply a with this, it is a factorial, and b with this, it is b factorial.
Right.
So it is clear that we can write this thing as this plus this, right?
Yes. Right.
By our induction step, we know that when a plus b minus 1 was equal, right now a plus b is n, but a plus b minus 1 would have been n minus 1, right?
Yes.
So when
Wait.
the sum is what?
No, 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 right.
Right now, currently we are doing this case, a plus b is n. In that case, a plus b minus 1 is n minus 1 factorial.
Right.
And these two things are adding up to that. So this fits the pattern that a factorial b factorial divides this for a plus b equal to n minus 1.
Yeah.
From the inductions assumption step, we can say that this is true. This is divisible. This is an integer. Similarly, this is also true, because this
Right.
is the case where it is n minus 1. Sum is n minus 1, and these two are adding up to that.
Right. Yeah.
Here also, here the sum is n minus 1, and then we know that a factorial b factorial divides this, and these two add up to this.
Yes.
So both are integers. So that means the whole thing is an integer, which means even in this case, when a plus b is equal to n, the result is true.
Yeah.
We have established the base case, we have assumed the induction step, and then we have proved that it is valid for the next higher case.
Correct.
So that is the induction proof. But obviously, the best proof is the combinatorial proof, where you can say that NCR means number of ways of choosing R things out of N things, and is obviously an integer. So here we are
Yeah.
choosing A things, or we are choosing B things out of A plus B things. And both of these expressions automatically give you that this by this is an integer.
Right. Yeah.
Okay. What about the next one?
The next one was prove that the product of n consecutive integers is divisible by n factorial. So, like, for this one, it says prove that they're divisible by n factorial. So you can write n factorial as like n times n minus 1, n minus 2, so on and so on. And then the product of n consecutive integers would be like, let's say, I don't know, a plus a times a plus 1 times a plus 2 all the way to a plus n minus 1. And then I was not really sure how to like simplify it down to get it submitted, but we can see that you have these like similar terms sort of.
We have to prove that this is an integer.
Yeah.
Let's say these are the n consecutive integers.
Hmm.
So this will come if you know the previous proof. For example, we know now that a plus b factorial is always divisible by a factorial b factorial.
Correct. Yeah.
So now you just need to make the top part a factorial. In order to make the top part a factorial, you need to write all the x plus 1, x plus n minus 1. So we need to write all the lower terms, right?
Yes.
X minus 1, x minus 2 till 1, right?
Right. Yeah. Yeah.
So if I have to add those numbers there, I will also have to add them here.
Right.
And now the top thing is the product of everything from 1 to x plus n minus 1, which means the top part is x plus n minus 1 factorial.
Right. Yeah.
The denominator is n factorial and x minus 1 factorial,
Yes.
which is obviously an integer because
Yeah.
you're
Oh, yeah. Mhm.
it is fitting the pattern of the previous thing, right?
Right. Yeah.
If you are able to prove this, then you can immediately say from here, all we did was make a factorial on top by adding the relevant missing numbers.
Right. Yes.
And we added them top and bottom, and the bottom part also became one more factorial, and the top part became x plus n minus 1. And it
Right.
is in such a way that the sum of these two numbers is adding up to this.
Yes.
Okay. Uh, Fine. So we'll do some questions from AMCs. So first one is LCM of n and 18 is 180, whereas GCD of n and 45 is 15. What is the sum of digits of n? N is a positive integer. Yeah, I'll write a couple more questions. Try these out.
Okay. Wait, for the first one, am I supposed to find like the smallest or biggest n or?
You're supposed to find out the sum of digits of n.
Oh, wait, is it 6? Because is 60 the answer?
Hmm. Okay, that is correct. Uh, okay. I don't know if we have done this question. Maybe we have done this question before. Number of 7 tuples of positive integers which satisfy, I don't know, just look at the question if you have done this before. Number of 7 tuples
I don't think I've done it. I don't recognize 7 tuples anywhere.
of positive integers such that you have to find how many such seven tuples you can make such that these three equations are true. And all of them
Okay.
have to be positive integers.
Yeah, okay. For the second one, is the answer 96?
Hmm. You just have to notice that 71 is a prime number, and
Yeah.
after that, just do factorizations. The possible values of these numbers will be, what are you getting?
Uh,
We
so
know
like,
that
huh?
C is common in the first two equations,
Yeah, so it has to be 1, and then so is E.
right? C is
So then,
1, E is 1, and after that the equations become much simpler.
yeah.
D is 71, obviously.
And then AB is 70. So, and there's 8 factors of 70, and then uh FG is 72, and there's 12 factors of 72. So then 8 times 12 just becomes 96.
Okay, next one.
Okay. Wait, for question number three, is A1, A2, A3, and then A3, A4, A5 different geometric sequences or part of the same?
They are different. We don't know. They have just said that they are both geometric sequences.
Yeah, okay, I was just making sure.
If they have not said they are same, then you have to assume it is different.
Yeah.
In question 3, if you know A3 and there are two different geometric sequences, you can write expressions for A1, A2, and A4, A5.
Yeah, I did A3. So for the first geometric sequence of A1, A2, A3. Well, no, I did the arithmetic sequence first. So we know that A3 is 1575. So then A5 is going to be 1575 plus some D. And then A1 is going to be 1575 minus D. And then I plug those in the geometric sequence.
The geometric sequences can be said to have common ratios of R and S. R for the first one, S for the second one. And
Yeah,
if that is the case, this is the way they should be, right?
right. Yeah.
Now you can use the arithmetic sequence result. A1, A3, A5 are in arithmetic sequence. So A1 plus A5 should be twice of A3, right?
Yeah.
So we'll get an equation like this, should be twice of A3. So twice of 1575. You can
Yeah.
cancel 1575 everywhere. You get 1 by R square plus S square is equal to 2, right?
Right.
Now let's see if there is any other information. So far, it doesn't seem like there is any other information. So now 1 by R square plus S square is 2. And we know some information, like we know that R square, for example, divides 1575 because all
Correct.
of them are integers.
Yes.
So if R square divides 1575, then it cannot be a big integer because it has to add up to 2 and these are positive, right?
Right. Yeah.
It has to be 1, right?
Yes.
So that is one of the situations that one of the things that you can figure out. So can 5 work? 1 second. 1 by R square. Okay, so what we can do is, what are the possible values of R square? It could be R square could be 1, could be 5, could be, if you divide by 5, you're getting 325. Could be other numbers also, bigger numbers, but then actually it cannot even be 5, right? Wait, R square could be 5 because 1 by R square has to be less than 2, right?
Yeah, but then I don't think
It's
S,
fine. The
but
bigger
then
the number you get, 1 by R square is going to be smaller, no?
but then wouldn't S square have to be like 24 by 25? Oh, wait, not 24, sorry. 48 by 25?
So that is what you have to check,
Oh,
that it
okay,
has
yeah.
to be an integer.
Yeah. Okay.
So R square possibilities are actually 1, 3, 5, and 15. 3 is also there. 1, 3, 5, 15 for R square. Because all of these cases will work because 1 by R square is anyway smaller than 2.
Yeah.
But not all of these cases will work to keep S square an integer.
Right.
You have to check when is S square also remaining an integer. So 1 obviously works because then S square is also 1.
Yeah.
So you get R square is equal to S square is equal to 1. 3, if you try, you will get 1 by 3. It is not going to work. 5, if you try, so R square is 5, so 1 by 5. So that also is doesn't seem to work.
Wait, wouldn't it be 1 by 25?
But we have 1 by r square, right? I'm talking about r square right now.
Yeah, so if r is, oh, if r squared is 5, okay. I thought you said r is 5.
Yeah, actually r square cannot be 5 because then this will not be an integer.
Yeah.
1 second. So what are the possible values of r such that both r and r square divide 1575?
R could be,
So yeah, r could be 5 actually.
yeah, and
R
then
could
r,
be 1, 3, 5, 15 because
yeah,
225 will also divide this.
right, yeah.
So in that case, you will get different values of s now. You have to calculate a little bit and check whenever s is an integer.
Yeah.
You will see that 1 and 5 works. And in those cases, if r is 1, s is also 1. But if r is 5, 1 by 25, you subtract that, you get 49 by 25. So s is 7 by 5 in that case.
Right.
And 7 by 5 is fine because that still keeps a4 and a5 as integers.
Yeah.
So then you can find out the possible values of mod of a4 minus a5, a2. One case it will be 0 because then r and s are both 1, then every number is same.
Oh, yeah, right.
The other case is the one that we need to care about where r is 5 and s is 7 by 5.
Yeah.
And in that case, you'll get the answer.
Right.
So the point is that you just have to get this equation and then you have to figure out a condition. You don't need to solve this equation. You have to just figure out whether a1, a2, a3, a4, a5 are all integers at all times. So there are only limited possibilities for R and S for that to happen.
Yeah.
You have to take all the possibilities that work and that will give you the answer.
Right.
Let's try out the next one.
Okay. Wait, what's the symbols? Like the sideways 9 on the n equals 2, 1, 1, 2.
It's just a symbol for sum of the divisors.
Oh, okay.
Sigma of n is 2112 is sigma of n stands for sum of divisors of n.
Oh, okay. And then the number of relatively prime integers and less than is that one. Pi of n. Okay.
This is sigma, this is pi.
Mm-hmm. Okay, all right. Thank you.
We know that n has 4 positive divisors. If you know how to count divisors, there are only some ways in which you can make n like that. Suppose n was p into q into r. These are prime numbers. How many divisors are there?
4.
No.
Oh, 5, because P, Q, R, N, and 1.
What about PQ, QR, RP?
Oh, yeah. So
You
it'll
don't
be
know a
like,
general way to count how many divisors are there for a number. You cannot keep listing them.
oh, it'll be, so P to the power 1, Q to the power 1, R to the power 1. So you add 1 to each, so it'll be 8 divisors.
So if n is p into q, how many divisors are there?
4. So yeah, I did that and I got that 1 plus P plus Q plus PQ is going to be equal to 2, 1, 1, 2. So then if you factor it, you get like P plus 1 times Q plus 1 is 2, 1, 1, 2.
Right? So n could be like this. N could also be, by the way, like this.
P to the power. Yeah.
Here
Yeah.
also number of divisors is 4, 3 plus 1.
Yeah.
So if there is only one prime factor, it has to be PQ. If there are two prime factors, it has to be like this, P into Q. It cannot
Yeah.
have three prime factors.
Right.
So these are the two ways in which n could have been. Now we know that the sum of its divisors is this. So now we can take the cases here. We're getting 1 plus P plus Q plus PQ is 2112. Or you could get here 1 plus P square plus PQ is 2112. Right?
Yes.
Now, given that the number of positive divisors, positive integers less than and relatively prime to n is phi n, which is 1932. Positive integers less than and relatively prime to n. So, if you think about it, how many positive integers are there which are less than n? N minus 1, right?
Yeah.
And out of those n minus 1, there are some of them which have common factors with n.
Yes.
We need to find the ones that are relatively prime.
Right.
So
Yeah.
what can we say about that? Uh, so basically, if there are two prime factors, all multiples of any prime factor will not work, right?
Right.
So we can say that P, 2P, and so on till some Kp such that Kp is less than n. Correct?
Correct.
All of
Yeah.
these have to be excluded. Similarly, Q, 2Q till LQ, where LQ is less than N. All of these also have to be excluded, right?
Right.
And you should realize that K is less than P and L is less than Q because Q square is not going to come, right?
Right, correct.
So these are the numbers which are relatively, these are the numbers which are not relatively prime to n, right?
Yeah.
Any other numbers will be relatively prime because they will not share these factors of p and q.
Yeah, right.
So think about how many there will be like this. So the numbers here could be p minus 1 into p, right? Up to p minus 1 into p.
Yes.
There will be p minus 1 of these because you cannot put a p square. There is no p into p, right?
Yes.
Similarly, there's q minus 1 of these.
Yeah.
Any combination of them also is not allowed. You can have numbers like p into 2q and things like that, right?
Yes.
So basically, you can say that as p minus 1 into q minus 1 possible ways to combine any of this with any of this, right?
Mm-hmm. Right.
These are the numbers that are having some, one second, relatively prime to minus 1932. So maybe we should look at some smaller numbers to get the pattern. So for example, uh, let's say n is product of two primes, let's say 7 into 11, 77, right?
Right.
Now here we cannot have 7, 14 till 77, till 70 because less than n. Till 70, we can also have 11, 22 till 66. There are 6 here and there are 10 here. And right, these numbers are less than n, less than 77, and are not relatively prime. They have common factors with 77. So, so how many are there? So 16, right? Actually, it doesn't make sense to multiply 7 into 22. All of these numbers will become bigger if you multiply. So 16 are there here. Uh, and you should exclude 1 also. Uh, so you get, I think, 60 numbers. 77 minus 10 minus 6 minus 1, right?
Right.
These numbers are coming which are relatively prime to 77 and are less than 77. And
Yes.
technically now you can see that that is same as p minus 1 into q minus 1.
Yeah.
Okay. So if we use that again here, we will say we already have equations like 1 plus p into 1 plus q is 2112. This is the sum of all the divisors, 1 plus p plus q plus pq. And we now
Right.
also have p minus 1 into q minus 1 is 1932, right?
Yes.
This is
Right.
phi of n, numbers less than n, but relatively prime to n. And here n was written in the form p into q, correct?
Right.
And this was our sum of all divisors, sum of all divisors of n, correct?
Yes.
So from these two equations, now we can try to find out what is the possible value of p and q. So 1 plus p times 1, let's factorize 2112. 2112 is divisible by 3 also. So 3 into, it becomes 704. 704 is, I think, it is divisible by 64. So 64 into 11. So it is 2 power 6 into 11. This is my 2112 number, correct?
Yes.
So what I want is a product of two numbers to be equal to this. So can we think of some good numbers which will fit this? So you have 33 into 2 power 5 is 36. So 64 into 33 is a possibility. You could also get 11 into 4. So why am I not choosing 64 into 33? Because I don't think that will fit the second equation. If 1 plus q is 33, q is 32. So this will be 31 and this would be 62, right? That
Yes.
is too big, I think. 1 second, maybe not. 62 into 31 is 2 into 31 square. 31 square is 961. Oh, it is fitting, right?
Right.
Is it fitting? 2 into 961.
Two
No,
two
it is
into
fitting.
61. Yeah, it is. Yeah. Wait, no. That's 1922, not 32.
966 would have been this. So it doesn't fit.
Yeah.
So, okay, so this doesn't fit. So you can choose another pair. We can get 44 and we have taken 4 from here. So we are left with 16 into 3, 48. So in that case, P and Q are 43 and 47. So this would become 42 and 46. So that would be 44 square minus 4, right? And
Yes.
44 square is basically 1600 plus 16 plus 320. Okay, so that is 1936 minus 4. So that fits, correct?
Yes.
So P and Q values are coming. P is 43 and Q is 47. We have done it by simple prime factorization and checking. Now that we know this, we can find the sum of proper divisors of n because our n was P into Q, right?
Right.
So proper divisors of n will simply be 1 plus P plus Q, but we cannot put PQ because proper divisors means that the number is smaller than the number itself, right? The
Yes.
divisor must be smaller. So we have to just do 1 plus P plus Q here. So that will be 1 plus 43 plus 47,
Right.
which becomes 91 finally. So the point here is that we have thought about and figured out a way to get how many numbers are less than a number and are relatively prime to it. Correct?
Yes.
Later we'll do theory about it, which will tell you a more general method. Right now we just sort of guessed a pattern, and from there we figured out this question.
Right.
But ultimately you have to learn about something called Euler's totient function, which is a generalization of this.
Okay.
And we'll also
So,
talk about Legendre's theorem. So these two things we'll discuss in the next class.
okay.
So
Wait, so is next class number theory or AMC?
it will be number theory only next class.
Okay.
So we'll do these two things and then we'll do AMC after that.
Okay. All right.
Okay, that's all for now then.
All right. Thank you.
Hmm.